Howdy, we're back. So let's look at an application of law of sines. It says to measure the height of a mountain, a surveyor takes two sightings of the peak at a distance of 900 meters apart on a direct line to the mountain. So there's our lovely picture. I will say sometimes you're not given a picture. Oof, that's the hard part, to be able to draw these. The first observation results in an angle of 47 degrees, and then the second of 35 degrees. If the transit, so here is 2 meters high, what is the height of the mountain? So as you can see, we're trying to find this height, and then of course we'll add the 2 meters. So putting that in our nice little triangle picture, this is what it would look like. So we need to figure out how to solve for h, meaning we need to solve for b and then add 2 meters. So let's see if we can do this. All right, so give me color. If I look at C, this is on a straight line with the 47 degrees. So I know C plus the 47 degrees must equal 180 degrees. And so therefore I can get that angle. All right, then I could actually find A now. So I'm going through and I'm solving for different pieces to be able to figure out how I'm going to get B. So I know A plus 35 degrees plus this 133 degrees should equal 180 degrees. So I'm in this first triangle, and therefore A equals 12 degrees. Okay, so now that I have something, I'm actually going to try to solve for little c. And I can do this with the sine of A, which is 12 degrees, over the side opposite A, which would be your 900 meters, and then the sine of 133 degrees over the opposite, which is what I'm solving for. All right, so if I solve this, doing all that crazy algebra stuff that you do, you should get that. So that piece is 3,165.86 meters. Now from here, first thing I notice is I had to use law of sines this step, but to be able to get B, isn't this a right triangle? Yeah. So I actually could, by looking at this angle, I could say the sine of 35 degrees, remember SOHCAHTOA is opposite over hypotenuse, which in this case is B over the 3165.86. And now I have something that I can actually solve. So B equals 3165.86 times sine of 35 degrees. And I get 1816 meters. And then don't forget to add the 2 meters here, plus the 2 meters. Now, if you didn't think about, but I always think about right triangles, you could have used law of sines, meaning I could have used the sine of C over little c, sine of B over little b. And so in this case, my C is 90 degrees. So sine of 90 degrees over the 3165.86. And then my B, the angle opposite, is the 35 over little b. And so if I solve this for B, guess what? I get the same answer. So at least nice to know that you can use either one in this case, but as soon as I see a right triangle, I kind of go straight to the right triangle. All right, so this is going to be an all slides one. So it says, in attempting to fly from city P to Q, an aircraft followed a course that was 10 degrees in error. After flying a distance of 50 miles in error, the pilot then corrected the course by turning at a point R and flying 70 miles further. If the constant speed of the aircraft was 250 miles per hour, how much time was lost due to the error? So here's one that you may have to draw. So once again, I can see that it shows here that there was a 10 degree, so right there, error. He should have went straight along here, but he turned. He went 50 miles, then he turned and he went 70 miles. So let's see what is the actual time of the trip. Well, if you remember, distance equals rate times time. I can solve for time equals distance over rate. So the time of his actual trip was the 50 miles, 70 miles, and then where'd the 250 miles per hour come from? Rock chair. So that was given. And so I get the time of the actual trip. Now what I need to do is try to figure out, well, what was the time if he didn't take this 10 degree turn? So I can solve the triangle. We have two sides, side, side, and an angle opposite one of the sides. So even though this is kind of laid down, that angle, the 10 degrees, is opposite. And so I have a side-side angle, and I can actually solve for this angle Q. So doing so, I plug in my sine of 10 degrees over the opposite leg, 70 miles, sine of Q, the opposite 50, and I actually get this for sine of Q, and then of course I have to do the inverse. So I do the inverse and I get the degrees. All right, so from here I can get the last degrees just to finish up this triangle, because as you can see, why would I need this degree? I need this side opposite of it. So I'm gonna have to use this. So I take the 180 minus the 10 and then minus the 7.125 I just found, and I get, we call this angle R. And so now from here, this distance from P to Q, I can actually solve because I have the angle opposite of it. And that's kind of the big key with these, is that you know what you need. The only way I can solve for this side is I have to have the angle opposite. And so I did all that and I get this length. So the trip should have been 118.7 miles. How much time, they asked me, was lost due to error. The actual trip, remember we computed the trip taken. If they did it right, should have been the actual trip 118.7 over the 250 miles per hour. And so as you can see, he lost 18.72 seconds, which could be a big deal if you're sitting at the airport waiting, right? All right, so that finishes law of sines. We will move next into law of cosines.